Hello, my name is Jack Rummler, and I am joined by my colleague Kate Tanabe as we explore flood inundation modeling using logistic regression in Calgary, Alberta, and Minneapolis, Minnesota. Flood inundation modeling is the process of simulating flood risk based on a variety of parameters that predict the probability of a flood event happening. These features can be hydrological, natural, or built environment characteristics of the study area. We use this approach to understand where and why flooding occurs. While traditional flood models may have more focus on depth and extent, flood inundation modeling seeks to predict the flow of water in a flooding event, allowing planners to visualize exact locations where flooding is likely to occur. As the ramifications of climate change increase, the impacts of flooding are likely to worsen, and planners must understand areas at greatest risk to mobilize resources, quantify social and economic impacts, and improve emergency management planning strategies. Our objective with the flood inundation model is to develop an accurate and generalizable model that can reliably forecast flooding across different contexts. Our model is built using flood inundation data from Calgary, Alberta, and is used to predict flooding in Minneapolis, Minnesota. We chose Minneapolis given similar characteristics in terms of population, predominant hydrologic features, and climates. We first look at where flooding occurred in Calgary and hypothesize several features that may contribute to flooding. We then built a fishnet, which is a grid of equally sized cells to create a uniform spatial surface to aggregate our dependent variable, flood occurrence, and our features into. We split our data into training and testing sets, meaning we train our model on 70% subset of the data and test it on the remaining 30% to obtain predicted probabilities. We complete a variety of diagnostics to validate our model, and then we use it to predict flooding in Minneapolis. Since we do not have flood occurrence data for Minneapolis, this tests our model's generalizability, but we cannot confirm its accuracy. The map in the top left shows our dependent variable, observed flooding. We chose 5 significant features to overlay into the fishnet. These include the predominant land cover of each cell and whether it is pervious or impervious, a binarized average slope change of greater than 5% or less than 5%, distance to the nearest park, distance to the nearest hydrological feature, and flow accumulation. These features were created using zonal statistics in ArcGIS and R, which is a statistical calculation of cell values in a raster. We repeat the fishnet and feature engineering process for Minneapolis. Again, we are only predicting floods based on shared features, but we cannot validate the accuracy without flood data for Minneapolis. We built our model of Calgary in R and trained it on 70% of our fishnet cells. This histogram shows the counts of predicted probability of flooding on the remaining 30% of cells our model was tested on, showing that our model has a heavy skew towards 0% probability. This makes sense considering how several cells did not experience flooding. Our model assigns a value from 0 to 100% on likeliness to flood. Then we choose a threshold in which probabilities above the threshold are assigned predicted to flood or a value of 1, and probabilities below the threshold are assigned not predicted to flood or a value of 0. Looking at our model metrics, our model does a near perfect job correctly predicting not flooded or 0 values that did not flood, with a specificity score of 98%. However, our model does poorly correctly predicting flooding on 1 values with a sensitivity score of 35%. Overall, we have an accuracy of 95%. While we believe this to be a strong accuracy score, the low sensitivity means we may be overlooking areas that are at increased risk and should be further explored to ensure all vulnerable areas are accounted for. Finally, we present our predictions for Minneapolis. While we cannot be certain that this is an accurate prediction, the predictions follow a similar spatial structure in terms of proximity to the major river, meaning our model is likely generalizable to other context areas. We believe that with improved feature engineering, tuning the parameters of our fishnet, and exploring different probability thresholds, we can improve the predictive power of our model and hopefully better prioritize at-risk communities. To gain more insight into our modeling and validation process, please check out the document in the description. Thanks for listening.